All right, in this video, we're going to talk about section 1.4 dealing with polynomial and rational functions. And in this video, we'll look at how to find the degree, the x-intercepts, and the y-intercept of a polynomial function. We'll graph and analyze rational functions. Also, we're going to find equations of asymptotes and graph rational functions. And we're going to solve applications involving polynomial and rational functions. First of all, let's define what a polynomial function is. And here's that definition. A polynomial function can be written as a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus and so on all the way to plus a sub 1 x plus a sub 0 for non-negative integer n, which is the degree of the polynomial. The coefficients a sub 0, a sub 1 all the way through a sub n are real numbers with a sub n not equal to 0. The coefficient of the terms a sub n x to the n, the highest degree, is called the leading coefficient. Okay, so keep in mind the degree of the polynomial is going to be the highest exponent in that polynomial function. Your leading coefficient, of course, would be the coefficient of the variable to the highest power. Okay, and the domain of a polynomial function is the set of all real numbers. Okay. The domain is a set of all real numbers for any polynomial function. The range, if your degree is odd, that means if you have a third degree or fifth degree, seventh degree, and so on, that range will be all real numbers. But for an even degree, like second degree, fourth degree, sixth degree, and so on, it's just going to be a proper subset of reals. Okay. The constant function has a polynomial of degree 0 because it's just a number. A linear function is a polynomial of degree 1, and the quadratic function is a polynomial of degree 2. Okay, now on the next page, I'm going to show you. In this case, it does show the graphs of representative polynomial functions of degrees 1 through 6, and the figure suggests some general properties of graphs of polynomial functions. So if you look here on the next page of your notes, you'll see these types of polynomial functions here. The first one you see is just a linear function. Its degree is of 1. That's the highest exponent. The one in the middle at the top, that is a third degree polynomial function, because that's x cubed minus 2x. And this one is a fifth degree polynomial function. As you can see, h of x equals to x to the fifth minus 5x cubed plus 4x plus 1. And that's what that graph looks like. Now, the ones on the bottom have even degree polynomial functions here, like this one, f of x equal to x squared minus 2x plus 2. That's the graph of the parabola, or the second degree polynomial function. And then this next one is a fourth degree polynomial function, 2x to the fourth minus 4x squared plus x minus 1. That's what that graph looks like. And this one is a sixth degree polynomial function. That's this one here. And here's some shared properties of odd degree polynomial graphs. All odd degree polynomials cross the x-axis at least one time. So if you look at these three graphs at the top, those are odd degree polynomials. You can see that they're crossing the x-axis at least once. All odd degree polynomials with positive leading coefficients start negative and end positive. Okay, odd degree and a positive leading coefficient pretty much is going to start negative, like this one right here, and it ends up positive. Same thing here with this one, starts negative and then ends positive. And all odd degree polynomials with negative leading coefficients start positive and end negative. Okay. So for this graph, it would be the other way around, like this. They'll start positive and then end negative. Okay. And the shared properties for even degree polynomial graphs. Some even polynomials never intersect the x-axis, like this one right here. This is an even degree polynomial function. You can see that it's not crossing the x-axis. All even polynomials that start positive and end positive have positive leading coefficients. So you can see here starting positive and then ends positive. This one starts positive and ends positive. This one starts positive and ends positive. Okay. And all even polynomials that start negative, end negative, and have the same, and have negative leading coefficients. If you have a negative leading coefficient with an even polynomial function, it's going to start negative and end negative. So we had a leading coefficient of a negative number, then that means for this even polynomial function, it will end up starts negative, ends negative. Now here's some observations about the graphs. Each odd polynomial graph started negative and ended positive. That means all had positive leading coefficients. The ends of each odd degree polynomial moved in the opposite direction. And each odd degree polynomial crossed the x-axis at least one time. Each even degree polynomial graph started positive and ended positive. They all had positive leading coefficients. Some even degree polynomials crossed the x-axis and some did not. The ends of each even degree polynomial moved in the same direction, up on both sides. Okay, and there are other observations as well. No graph crossed the x-axis more than their degree. Changes in directions are limited to one less than the degree. In other words, let's take this one right here. This one is like an x to the 6, which is the highest degree or the highest power. So that means the change in direction is no more than 5 times. So here's one term, there's 2, 3, 4, and then 5. For a 6-degree polynomial function, there's no more than 5 changes in direction. Okay. And also, the other one where no graph crossed the x-axis more times than their degree, that means here, if this is a 6-degree polynomial function, that means it cannot cross the x-axis more than 6 times. Or for a 3rd-degree polynomial function like this one, it's crossing the x-axis 3 times, and that's the most that this graph will cross the x-axis, meaning there's only a maximum of 3 x-intercepts here. Okay. Now, polynomials are considered to be continuous functions. Graphs of polynomials are continuous and smooth, meaning that one can sketch all points on the graph without lifting the pen from the paper. And the graph has no sharp corners. And also, there are no breaks in the graph. That means, of course, drawing it without lifting the pencil off the paper. Here's some examples here. This one that you see here is not continuous because there is a break in the graph at x is equal to 0. And this graph in the middle is also, it is continuous, but it's not smooth. The reason why it's not smooth because you got that sharp corner at the point 0, -3. So this would not classify as a polynomial function. This one is, because as you can see, it is smooth and is continuous, meaning that there are no breaks in the graph, and the graph can be drawn without lifting the pencil off the paper. Okay. All right, now let's start with some examples of some polynomial functions here and answer questions about those. Like this one. For the given polynomial function, find the degree of the polynomial, all your x-intercepts, and all the y-intercept. In this case, you've got f of x is equal to 5x plus 6. F of x is equal to 5x plus 6. Well, first of all, the degree of the polynomial function, the highest exponent for x in that function for x is going to be 1. Because this is understood to be a 1 for the exponent of x. So this is a first degree polynomial function. So if we were to answer that question, it would be something like, in this case, just a first degree. Because they can just ask for the degree of the polynomial is just a 1. Okay. Part B is finding all x-intercepts. If you recall, anytime you're finding the x-intercept, you let your f of x be equal to 0. You let f of x be equal to 0. And it would help if I do it over here somewhere to the right. Okay. So here we're going to let f of x be equal to 0. And f of x is that 5x plus 6 equal to 0. To solve for x, we subtract 6. That will mean 5x is equal to -6. Divide both sides by 5. Your x will be -6/5. So your x-intercept in this case will be -6/5. And I think you just type that in as just that number itself and not as an ordered pair. And then for the y-intercept, we always let x equal 0, if you recall. So that means we just substitute 0 in for x. So it'll be f of 0, which is equal to 5 times 0 plus 6. 5 times 0 is 0. 0 plus 6 is 6. So the y-intercept there would be 6. Okay. So that's all we had to do there, was just simply find the degree of the polynomial function, which is 1, your x-intercept, which is -6/5, the y-intercept will be 6. All right, the next example is a quadratic function. Here you've got f of x equal to x squared plus 3x minus 4. And from that, we want to find the degree of the polynomial function, the x-intercept, and the y-intercept. So here, we're looking for the degree of that polynomial function. And the degree of the polynomial function is the highest exponent in that function. In this case, the highest exponent is a 2. So that means this is a second degree polynomial function, or a polynomial function of degree 2. Okay. Part B is finding the x-intercepts, or all x-intercepts. So we always set the function f of x to be equal to 0. And of course, now f of x is x squared plus 3x minus 4 equal to 0. Now with this, we can factor the left-hand side into two binomials. If we couldn't, we have to use the quadratic formula. So I'm going to factor this into two binomials here. So x squared will break up as x and x. The middle term is a plus and the last term is a minus, so one has to be plus, the other one has to be minus. Now we need factors of 4 that will give me 3x as a middle term. It will have to be 4 and 1. And the 4 will have to be plus because the middle term is a plus. And the 1 has to be minus. That way, 4x minus 1x will give me 3x. So I get x plus 4 times x minus 1 equal to 0. And then we set each binomial factor equal to 0. So it'll be x plus 4 equal to 0, and x minus 1 is equal to 0. And then next we solve each equation for x. So for the x plus 4 is equal to 0, that would mean x is equal to negative 4. And then for the x minus 1 is equal to 0, that would mean x is equal to 1. So these are my x-intercepts, negative 4 and 1. Okay. And they just want these as just whole numbers here in this case, negative 4, comma 1. So that's part B. Part C is finding the y-intercept. Anytime you find the y-intercept, you always substitute 0 in for x in this function. So f of 0 in this case would be 0 squared plus 3 times x, which is 0, minus 4. All right, if you square the 0, that's 0, plus 3 times 0 is 0, minus 4. 0 plus 0 minus 4 ends up being negative 4. So your y-intercept for this polynomial function would be negative 4, meaning that the graph crosses the y-axis at negative 4. Okay. All right, here's another example. For the following function, well, in this case, we're going to find the degree of the polynomial function, the x-intercepts and the y-intercept. In this case here, we got f of x is equal to 2x plus 3. That quantity is to the 4th power times the quantity x minus 2 raised to the 5th. And here I want the degree of that polynomial function. Well, it would take a lot of time to work all this out to get that degree. However, if you look at your exponents here, the 4 and the 5, that would give you the degree of that polynomial function. If I add 4 and 5 together, I would get 9. That would mean the degree of that polynomial function is 9. So I have a 9th degree polynomial function. Okay. That's pretty much a quick way of finding out what the degree of that polynomial function is. Now, part B is finding the x-intercepts, finding all the x-intercepts. To do that, you take your f of x, set that equal to 0, which means I have 2x plus 3, that quantity to the 4th, times the quantity x minus 2 raised to the 5th equal to 0. So in this case, I set each binomial factor equal to 0 because, of course, it's already factored completely. So that means I have 2x plus 3, the quantity raised to the 4th equal to 0, and x minus 2, that quantity raised to the 5th equal to 0. Now I'm going to solve for x. So for the quantity 2x plus 3 raised to the 4th, to get rid of that power of 4, I need to do the 4th root on both sides. And notice I'm not putting a plus or minus here because of the fact that 0 is neither positive nor negative. So that means I'll be left with 2x plus 3 on this side equal to 0. And then to solve for x, we subtract 3 on both sides. That would give us 2x is equal to negative 3. Divide both sides by 2. You'll get x is equal to negative 3/2. So that's one of the x-intercepts. The other x-intercept from x minus 2, that quantity raised to the 5th equal to 0. This time, to get rid of the exponent of 5, I need to take the 5th root on both sides of this equation. So that means I'll have x minus 2, well, x minus 2. X minus 2 equal 0. And if I add 2 to both sides, you'll get x is equal to 2. So these are my two x-intercepts here. X equals negative 3/2 and 2. X equals negative 3/2 and x is equal to 2. And then part C is finding the y-intercept. So to find the y-intercept, we just substitute 0 in for x in that polynomial function here. So I have f of 0 is equal to 2 times 0 plus 3, and that quantity is to the 4th, times x, which is 0 minus 2, that'll be raised to the 5th. Now let's simplify what's in the parentheses. 2 times 0 is 0 plus 3 is 3. So I have 3 to the 4th times 0 minus 2, which is negative 2, raised to the 5th. All right, 3 to the 4th, that's 81. Of course, 3 hat key and then the 4, that's 81. Parentheses negative 2, close parentheses, hat key, raised to the 5th, that's negative 32. And 81 times negative 32 will give me negative 2,592. That will be the y-intercept for this polynomial function. Okay. All right, next we'll look at regression polynomials. Now, back in section 1-3, it outlines the process of quadratic regression, one type of regression polynomial used to model sets of data. Most graphing calculators include other types of polynomial regression as best fit models for sets of data, like in this example here. Here we got a table to the right that shows the per capita consumption of ice cream and eggs for selected years since 1980. Here we're going to complete parts A and B. So in part A, we're going to let X represent the number of years since 1980 and find the cubic regression polynomial for the per capita consumption of ice cream. So we're not going to worry about the eggs right here. We're just going to be dealing with ice cream here. Now you're given the year, the actual year, but we need to convert that to a value since 1980. In other words, what that means here is this. If I subtract 1980 from this 1980, it's going to be 0. 1980 from 1995 would be 5. 1990 from 1980 will be 10. 1995 minus 1980 will be 15. 2000 minus 1980 will be 20. 2005 from 1980 would be 25. 2010 minus 1980 would be 30. That represents the number of years since 1980. And if you recall, when we were using the graphing calculator, we had to put this, the number of years, in L1. And here for ice cream in pounds, we're going to put that in L2. Don't worry about the number of eggs in that last column. We're just going to focus on these two columns here. So with our graphing calculator, here's what we're going to do. We're going to press the stat key. We're going to edit. We're putting in a brand new table. So we're going to select number 1 for edit. Now notice I got some stuff in L1 and L2. So to clear that out, what you're going to have to do here is this. I'm going to use my left and right arrow keys to maneuver over to, in this case, I'm going to use my left arrow key to go over to L1, use the up arrow key to highlight L1, then press clear and enter. Then I'm going to go over to L2 using the right arrow key, use my up arrow key to highlight L2, press clear and enter. So now my columns are cleared. So in the first column, L1, I'm going to put in these values that represent the number of years since 1980. So we're going to start with 0, then enter, and then 5, enter, 10, enter, 15, enter, 20, and then enter, 25, enter, 30, and enter. Had to press enter after the very last number. Then use the right arrow key to go to L2 and enter these values for L2, which represents the ice cream in pounds. So it'll be 17.5, enter, 17.7, enter, 14.9, enter, oops. Let me clear this out. 17.7, I'm sorry, then enter, 14.9, and then enter. Let's see, 15.3, enter, 16.1, enter, 15.2, enter, and then finally 14.1, enter. You want to make sure that you have the same number of data values in L1 as you do for L2 because each one of those correspond to each other. What's in L1 corresponds to L2. All right, now, what they want is the cubic regression polynomial. The cubic regression is what they're looking for. So what I'm going to do is second and mode to go back to the home screen. Then I'm going to press the stat key, right arrow to calculate. And if you look under number 6 is cubic regression. So I'm going to use my down arrow key to go to cubic regression and then press enter. X list will be L1, which is what I have. Y list will be L2. You want to make sure that L1 represents your X list and L2 represents the Y list. Now the frequency list and the story regression equation, those are going to be left blank. I'm going to go down to highlight calculate and press enter. Okay. So this is what I come up with as an answer. And of course, this is going to be e to the 4th. I'm not sure why they would use that, but I'm going to show you how to convert that into a into scientific notation. Because in this case here, negative 4.666 e to the negative 4 means in this case here, I need to move this decimal point 4 places to the left. So I only got room for 1. I'm going to need 1, 2, 3 zeros. There's only got room for 1. So it'll be 466, negative 0.000466. Now let's see how they want us to round this off to 4 decimal places. So if I have negative 0. This right here, that's the 4th digit after the decimal point. To the right of that will be 6. So it'll be negative 0.005. I mean 0.0005. So here, like this at the bottom, y is equal to negative 0.0005. 0.05 x cubed, because of the x cubed here. And then what's for x squared? That's going to be the b. To 4 decimal places, that would be 0.0228 x squared. And then plus for c, that's going to be negative 0.373, negative 0.3876. Okay. That's going to be the coefficient of x plus the constant. And the constant in this case is 17.9048. All of these are rounded to 4 decimal places. So this represents the equation, or the cubic regression equation for this situation. Because if you remember, the cubic regression is this: y is equal to ax cubed plus bx squared plus cx plus d. And in this case, they had that up here at the very top of the screen. So that's our cubic regression equation, which is the answer to part A. Now, part B is to use use the polynomial model from part A to estimate to the nearest tenth of a pound the per capita consumption of ice cream in 2025. Well, let's find out what X is, because X represents the number of years since 1980, and we're dealing with 2025. So let's subtract 1980 from 2025. That would mean X will have to be equal to 45. So that means Y is going to be equal to this: negative 0.0005 times X, which is 45, and that's going to be cubed, plus 0.0228 times X, which is 45, will be squared, plus negative 0.3876 times 25, plus 17.9048. Okay. Now this we can just go ahead and type in the calculator. So let me clear this out. Okay, y'all gonna have to forgive me for this. So it'd be negative 0.0005, parentheses, 45, close parentheses, the hat key, and then cube, right arrow to get out, plus 0.0228, parentheses, 45, close parentheses, x squared to square it, plus, and this would be negative 0.3876, close open parentheses, 45, close parentheses, and that should be 45, not 25. Because I'm replacing the x with 45. Okay. And then plus 17.9048. Now we're going to round this up to 1 decimal place, so this will be approximately 1.1. And in this case, it'll be 1.1 pounds of ice cream. So per capita consumption of ice cream in 2025 would be approximately 1.1 pounds. Okay. All right, so that's how we use that regression equation. and how we use our calculator to come up with the cubic regression equation and simplify. All right, next we'll look at rational functions. Rational functions. So here's the definition. A rational function is a function that can be written as f of x is equal to n of x divided by d of x, where your d of x, which is your denominator, cannot be equal to 0. And n of x and d of x are polynomials, by the way. All right, the domain is the set of all real numbers for which d of x is not equal to 0. In other words, you want to find out what values of x that would give your denominator 0, and you will exclude those. So, domain is just going to be those numbers where the denominator, the set of all real numbers where the denominator is not equal to 0. And rational functions are quotients of polynomial functions. All right. Now, in rational functions, you may have something called vertical asymptotes. That's what we'll look at here. A vertical asymptote of a rational function called f of x is a line of the form x is equal to b, which the graph of the function approaches but does not cross. Okay, so here's some illustrations of just that. In this first graph, you'll see that f of x has a vertical asymptote at x is equal to 2. Here's that vertical dotted line going through the x-axis at 2. You'll see that the graph gets closer and closer to your vertical asymptote, but it will never cross that vertical asymptote. The second one, here, this is the graph of f of x is equal to 8 divided by x squared minus 4. Here we have two vertical asymptotes. One is at x equal negative 2, and the other one is at x is equal to 2. So in this case here, you'll see those the graphs, they get closer and closer to your vertical asymptote, but it will never cross that vertical asymptote. And the third one, f of x equals to x plus 1 over x, doesn't have a vertical asymptote. It has what they call a slant asymptote. Yeah, a slant asymptote. All right, next we'll look at horizontal asymptotes. Since they're vertical asymptotes, we also have horizontal asymptotes. A horizontal asymptote of a rational function is a line of the form y equal k, which the graph of the function approaches but does not cross as both x increases and decreases without bound. And of course, the illustration of that is on the next page. So for this first graph here, we have a horizontal asymptote at y is equal to 1. So here's the horizontal asymptote there at y is equal to 1. You see it gets closer and closer to the horizontal asymptote, but it will not cross the horizontal asymptote. The second one has a horizontal asymptote at the x-axis, which is, of course, y is equal to 0. Again, you'll see that on the ends here, it gets closer and closer to the x-axis, but it won't cross that x-axis. And this last one does not have a horizontal asymptote at all. All right. Now, let's talk about vertical asymptotes of rational functions. If the denominator d of x of a rational function has degree n, the rational function can have no more than n vertical asymptotes. In other words, let's go back to this here. Excuse me. My denominator, x minus 2, the highest exponent is a 1. That means that there's only one vertical asymptote. For this one, x squared in the denominator, highest exponent is a 2. That means that there are only 2 vertical asymptotes and no more than that. Now, if the numerator, n of x, and the denominator, d of x, of a rational function have no common real zeros, then if d of z is equal to 0, then x is equal to c, which is a vertical asymptote of that rational function. All right, what they mean by common real zeros, when you factor it out, that means you probably, well, I'm sorry about that. No common real zeros. If the numerator n of x and the denominator d of x is the other rational function have common real zeros, they share linear factors for each shared real zero, and the rational function can be reduced by, and I would say, dividing out those common factors. Any remaining zeros for the denominator of the reduced rational function will be the vertical asymptote. So you want to make sure that your numerator and your denominator, if they have common factors in it, you can divide those out. And then what's left in the denominator, you can just set that equal to 0 and then solve for x, and that will tell you what your vertical asymptotes will be. All right. Now for the horizontal asymptotes of rational functions. A rational function with numerator degree less than the denominator of the degree has a horizontal asymptote of the equation y equals 0. In other words, if the highest exponent in the numerator is less than the highest exponent in the denominator, that means automatically you have a horizontal asymptote of y is equal to 0. A rational function with numerator degree equal to the denominator degree has a horizontal asymptote of y equals a over b. That's for the numerator leading coefficient a and the denominator leading coefficient of b. In other words, if the highest exponent in the numerator is the same as the highest exponent in your denominator, then you're going to look at your leading coefficients in the numerator and the denominator and divide that. It will be a over b equaling to y. That will be your horizontal asymptote. A rational function with numerator degree greater than the denominator degree of the denominator, it has no horizontal asymptote. In other words, if the highest exponent in your numerator is greater than the highest exponent in your denominator, there's no horizontal asymptote for that rational function. Here's some examples of this. For the given rational function, we're going to find the x-intercepts of the find the intercepts of the graph, both the x and the y-intercept, determine the domain, find any vertical or horizontal asymptote for the graph, and then graph y equal f of x using a graphing calculator. Okay, so here's what we have here. F of x is equal to 6 minus 3x divided by x minus 8. So let's first find our x-intercepts. And y-intercept. So let's start with the x-intercept. So here we set f of x to be equal to 0. So this f of x will be 0, and that's equal to 6 minus 3x divided by x minus 8. So in this case here, if I do, let's put 0 over 1 and do some cross multiplication. 0 times that x minus 8 would just still be 0, equaling to 1 times 6 minus 3x would be 6 minus 3x. And what I'm going to do is move that minus 3x over to where that 0 is by adding 3x to both sides. That way I won't have to deal with a lot of negatives here. This will be 3x is equal to 6. Divide both sides by 3. You'll get x is equal to 2. So your x-intercept is just going to be 2. Now for the y-intercept. Anytime you're finding the y-intercept, you substitute 0 in for x in that rational function. So we're going to evaluate f of 0. That's going to be equal to 6 minus 3 times x, which is 0, divided by x, which is 0 again, minus 8. So 6, let's do this. 3 times 0 is 0. 6 minus 0 is 6. 0 minus a negative 8 is negative 8. And if I reduce 6 over negative 8 in simplest form, it will be negative 3/4. So the y-intercept there would be negative 3/4. So all of this is part A. Part B is to determine the domain. Well, anytime we want to identify the domain, we take that denominator and set it equal to 0 because we want to find out what values of x that would give us a 0 in that denominator. And our denominator in this case is x minus 8. We'll set that equal to 0 and solve for x. So if I add 8 to both sides, you'll get x is equal to 8. So that means here, the domain is going to be all real numbers except 8. All right, part C. Find any vertical or horizontal asymptotes. Well, in this case here, the vertical asymptote we've already found, because this does not have any common factors in this problem for us to divide out. So the x is equal to 8, and there's only one vertical asymptote, because notice the highest exponent there is a 1 in the denominator. So that means there's only one vertical asymptote, which is x is equal to 8. Now for the horizontal asymptote, okay, now let's look at the highest exponent in the numerator. And I'm going to label this as n for the degree of the numerator and m as the degree of the denominator. The highest exponent in the numerator, here's the x, the highest exponent there is a 1. In the denominator, x minus 8, the highest exponent for the x is a 1. Notice that n and m are the same. So that means I need to look at the leading coefficients in the numerator and the leading coefficient in the denominator. Now, I can rewrite this numerator as negative 3x plus 6. This would be over x minus 8. This may help. The leading coefficient in the numerator, that's the coefficient of the variable to the highest power. If the highest power is a 1, that leading coefficient there must be negative 3. Divided by the leading coefficient in our denominator. That's the highest exponent. I mean, the coefficient of the variable to the highest exponent. That's going to be a 1, an understood 1. So y equal negative 3 over 1, which is negative 3. So the equation y equal negative 3 would be your horizontal asymptote. And then next we're going to do the graph on the graphing calculator. Okay, so if I go to y equal 2, and I'm going to clear these equations that I have in y1 and y2, the numerator is going to be 6 minus 3x. That would be put in parentheses. So I'm going to do left parentheses, 6 minus 3, xc theta for the x, and then close parentheses. Divided by, the denominator is x minus 8, left parentheses, x minus 8, close parentheses. Now I'm going to go to my window because in your homework, they're going to give you a choice of answers. You just have to pick the graph that best fits the one that's on your calculator. And they do give you dimensions to use. Like in this case here, for your x, you have to use negative 30 to 30. So x min would be negative 30. Y min would be positive 30. And I would do this in increments of 5, just to be on the safe side. And then for y min, negative 30. Y max will be 30. And then y scale will just be 5 as well. And after that, I'd go ahead and press graph. And now you see what that graph looks like. And pretty much you just have to select the graph that's the same as this one right here. Okay. But that's how you do the graph in the graphing calculator, and you'll have to select the one as the correct answer choice in your homework. Okay. All right, here's another example. We're going to be dealing with horizontal asymptotes here. This is just practice of how to find the horizontal asymptote based on those rules that I gave you. Let's say I want to find the equation for a horizontal asymptote for this function below. Here we got f of x equals to 4x to the fourth plus 5x plus 5 divided by 3x to the fourth plus 5x minus 5. All right, so we look at the highest exponent in the numerator and the highest exponent in the denominator. The highest exponent in the numerator is going to be 4. The highest exponent in the denominator is also 4. So here, your degrees are the same. So that means we can get our horizontal asymptotes from these leading coefficients of the variables to the highest exponent. So that means y is going to be equal to a over b. Your a is the coefficient of the variable to the highest power in the numerator. That's in this case going to be 4. The denominator will be the coefficient of the variable to the highest power in the denominator. That would be 3. So the equation y is equal to 4/3 is your horizontal asymptote. Okay. All right, here's another example of finding the horizontal asymptote of this function f of x is equal to 5 minus 4x plus x squared divided by 2 plus 5x plus 6x squared. Now, if you want to rewrite this, you can rewrite this as f of x is equal to, now put the x squared first, and then minus 4x, and then plus 5. I'm just writing this in descending powers. The denominator, the same thing. Write that as 6x squared plus 5x plus 2. And then we can identify n and m. Your n is the highest exponent in the numerator, that's 2. Your m is the highest exponent in the denominator, that's also 2. Again, n and m are equal to each other, so that means here we'll look at y is equal to a over b, where a and b are your leading coefficients. The leading coefficient of the variable to the highest power in the numerator will have to be that understood 1 over the denominator. We look at the coefficient of the variable to the highest power in the denominator. That's 6. So here we have 1 over 6. So the equation y is equal to 1/6 would be your horizontal asymptote. Okay. All right, on the next page deals with equations of any vertical asymptotes here. In example 8, we got f of x equals to x squared plus 6 divided by x squared minus 36 times x squared minus 9. And here we want to find the equations of the vertical asymptotes, if there is one. And in this case here, there are. Because if you look at your denominator, it's already factored out completely. So we take what's in that denominator, set it equal to 0. So we're going to set x squared minus 36 times x squared minus 9. That would be set equal to 0. And then we solve for x. Well, we're going to set each binomial factor to be equal to 0. So that means we're going to set x squared minus 36 to be equal to 0, and x squared minus 9 to be equal to 0. Each equation will solve for x. So for the x squared minus 36 equal to 0, if we add 36 to both sides, that means x squared is equal to 36. Now to solve for x, we're squaring it, so we need to take the square root on both sides, and we must include plus or minus when we take a square root on both sides. So that means x is equal to plus or minus the square root of 36 is 6. And then for the x squared minus 9 equal to 0, if I add 9 to both sides, that means x squared is equal to 9. And again, I'm going to take the square root on both sides and include a plus or minus symbol. So the square root of x squared will be x equal to plus or minus the square root of 9 is going to be 3. Now what this means here is this: I have 4 vertical asymptotes. Okay. That means x is equal to, and I'm going to put this in order from left to right. The smallest is -6, so it'll be x equal -6. And then x is equal to -3, x is equal to +3, and x is equal to +6. Now you may write those out as x equals 6, then x equal -6, and then x equal 3, x equal -3. But in the homework, they want you to put it in order from left to right, from the smallest to the largest, like I have here. Okay, here's another example. Find the equations of any vertical asymptotes for the function below. In this case, you get f of x equal to x squared plus x minus 6 divided by x squared minus 2x plus 5 minus 15. We're finding the vertical asymptote. That means we want to first find out what values of x that would give us a 0 in the denominator. And we want to make sure that there are no common factors. Okay, that's very important. Here we were fortunate with this problem because there were no common factors here that we could have divided out. But let's check this one. All right. If I factor x squared plus x minus 6 into 2 binomials, let's see, x here and an x here. One will have to be plus, the other one has to be minus. Factors of 6 that would give me a positive x, 1x would be 3 and 2. And it has to be x plus 3 and x minus 2. Now for the denominator, x squared minus 2x minus 15. One's got to be a minus, the other one has to be plus. The factors of 15, that gives me a minus 2x will be minus 5 and a plus 3. Now notice we do have common factors in the numerator and the denominator. So that means we need to divide out these common factors, x plus 3. And if we simplify it, it would be x minus 2 divided by x minus 5. Okay, that's after dividing out your common factors. Now from this, we can identify our horizontal asymptote by taking that x minus 5, setting it equal to 0, add 5 to both sides, you get x is equal to 5. So your vertical asymptote will be the equation x is equal to 5. Okay, so this is one of those cases where you have to first find out if you have any common factors in the numerator and the denominator. And if you do, factor each numerator and denominator and divide out your common factors if you have them. And then determine what your your vertical asymptotes will be. Okay, so that's very important. Okay, last example in this video. For the given function, or the given rational function, I should say, f of x is equal to 16 minus 4x squared divided by x squared minus 16. First of all, you want to find any intercepts for the graph, both the x and the y-intercept, find any vertical and horizontal asymptotes for the graph, and then graph the function in a standard window using a graphing calculator. All right, so let's see what we have here. First of all, let's find out x-intercepts. So that means I take that function, set that equal to 0. So that means f of x will be set equal to 0, equaling to 16 minus 4x squared divided by x squared minus 16. Now I'm going to treat that 0 as 0 over 1 and do some cross multiplication. So 0 times x squared minus 16, that's going to be 0, equaling to 1 times 16 minus 4x squared would be 16 minus 4x squared. All I'm doing there is just cross multiplying. Now I'm going to move the 4x squared over to where the 0 is. So I'm going to add 4x squared to both sides. So it'll be 4x squared is equal to 16. And then divide both sides by 4. You'll get x squared is equal to 16. X squared is equal to 4. And then if I take the square root on both sides, I'll include that plus or minus symbol. That means x is equal to plus or minus 2. So here I got two x-intercepts. One will be at x is equal to 2, and the other one is at x equal negative 2. Okay. Before I go to part B, I need to find the y-intercept. That says find any intercepts. And that means x-intercept and y-intercept. To find the y-intercept, we just substitute 0 in for every x in that function. So that means f of 0 is equal to 16 minus 4 times x, which is 0, and that's squared, divided by 0, that's squared, minus 16. Just substituting each x with 0. 0 squared is 0 times 4 is 0. 16 minus 0 is 16. Divided by 0 squared is 0, minus 16 is negative 16. 16 divided by negative 16 is 1. Negative 1, I should say. So the y-intercept is going to be negative 1. So all of that is part A. All right, now part B is finding any vertical and horizontal asymptotes for this graph. All right, now for this function right here, I'm going to rewrite this. Let's see if I could factor out a negative 4. I'm just trying to see if I have any common factors here. That would mean now I have a positive x squared minus 16. Over x squared minus 16. Oh, I'm sorry. This should be minus 4. Because I factor out the 4. And 4 goes into 16 4 times. All right, now let's factor x squared minus 4 into two binomials, x plus 2 times x minus 2. the denominator x squared minus 16 will be x plus 4 times x minus 4. Notice that there are no common factors here to divide out, so pretty much we can just go ahead and take that denominator of x plus 4 times x minus 4 and set that to be equal to 0 to find out what our vertical asymptotes will be. So that means, in this case, x plus 4 is equal to 0, and x minus 4 is equal to 0. Each equation will solve for x, so for the x plus 4 is equal to 0. If I subtract 4, you'll get x equal to negative 4, and then for x minus 4 is equal to 0. If I add 4, you'll get x is equal to 4. So these are my two vertical asymptotes at x equal negative 4 and x is equal to 4. And then, and by the way, I'll just label these as vertical asymptotes. And now for the horizontal asymptote. N is always going to be the highest exponent in the numerator, and m is going to be the highest exponent in the denominator. Looking at this, the highest exponent in that numerator is going to be 2. And then the denominator, that highest exponent is the understood 1. The highest exponent in the denominator is a 2. They're both equal to each other. So that means we look at our leading coefficients of y is equal to a over b. Highest exponent is a 2. Its coefficient is, notice, negative 4. Divided by highest exponent is a 2 in the denominator. Its leading coefficient will have to be that understood 1. So negative 4 divided by 1 would be negative 4. That would mean the equation of y equal negative 4 would be your horizontal asymptote. All right. And now for part C is using the standard window. And you'll be given a choice of graphs here to use. To choose from, I should say. So let me go to y equal to and clear this equation out. That 16 minus 4x squared would be in the numerator. So I'm going to do left parentheses 16 minus 4. Press the xt theta for the x and then x squared on your calculator. Then close the parentheses. Divided by, and then left parentheses for your denominator. X squared, press the xt theta for the x. Hit your x squared button to square for the exponent. Minus 16. Close parentheses. Now for the standard window, I'm going to press the zoom key and then select number 6 for the standard window, zoom 6. Now my calculator doesn't give me the vertical asymptotes here, but this is what the graph of that rational function f of x equal to 16 minus 4x squared divided by x squared minus 16 will be. Okay, and you'll choose the one that's similar to what you got on the calculator for that. Okay. All right, so that does conclude this video on section 1.4 dealing with polynomial and rational functions. Feel free to reach out to me if you have any questions about any of the problems that were presented in this video or any of the homework problems in my math lab on this section.